you already have seen your syllabus, right? In this syllabus, you will find that in electric drives, there are mainly two parts. One part is regarding some calculation, just a minute, calculations, then stability analysis, then heating, cooling, all those things. And the other part is actually electronic drive part. Now, as regards your say, things are concerned, so basically these two parts are very critical in the sense that you will see whoever will be going to industries. I don't know in this scenario. Industries means mostly are industries, but anyway, after some 1 or 2 years also, you will find some opportunity maybe to go to some core industries, where you will find that majority of the application of electrical engineering, whatever you have read, are behind this portion, drives portion mainly. Because see that I think I am repeating maybe if you have heard it or not. So while generating electricity, actually, you will find that mainly rotational energy, or you can say rotational kinetic energy, is actually converted to electricity. Majority, 80 to 90%, 10% only are from other sources like solar, etc., etc. And while consuming electricity, also you will find that 90% of this consumption are made from this motors, made by the motors or electric motors or rotating machines, you can say. If you divide the total load, maybe in industries or anywhere, if you divide the total load, you will find that categorically there are mainly three types of loads categorically, right? One load is this load, motor load, right? It is about having a share of 75 to 80%, right? And the other one is heating load, heat generation, right? By maybe some heaters, maybe some furnaces, etc. That is around 10%. And the other one is lighting load. So it is another 10%. So majority, maybe there are various types, few types, maybe there 1 or 2%, but you see that if you divide, so then it's the myth that we generate by rotation and we actually consume by rotation. So therefore, I mean, whoever will be going to the industries will be facing this type of say, drive systems, or maintaining drive systems, or designing drive systems. If you join some core industries, even like ABB, Siemens, etc. So nowadays, even they are coming behind some renewable sources like say induction generators, turbines, systems, and all. So that also rotation. So then you please concentrate on the subject a little bit, so that in future whoever will be staying in this field, right, say electrical engineering core, will be needing this basic knowledge of this. Of course, in the classes, you will never get 100% knowledge. When you go to industries, you will find that these are only the foundations. So you have to build from there. Anyway, so then you see that the syllabus is divided into two parts, and drives part, core drives part, this one, we have mainly three types of motor drive systems. One is actually induction motor, another is DC motor, and the third one is synchronous motor drive system. And after that, some few schemes like protections, etc., are there. So I think we'll try to cover every aspects of this drive system in this class. If we a little bit say, if you are attentive and if you are a little bit, if I miss 1 or 2, then you can compensate with other extra classes. That will help it. So actually, we'll start with induction motor drives. You know, this is the even the motors, among the motors, you will find that 85% again are induction motors, industrial motors, if you see. So this has got major importance and major stress also. So there are, I mean, lots of developments are going on. So you will not be, I mean, getting in this class up to that extent, because the limitation of the syllabuses and your basis of understandings also. So then we start with induction motor drive system. Okay. So I think the slide is visible and I am also audible to you clearly. Nah? Hello?
Yes, sir.
Okay, okay, just a minute. So if you look at speed control of induction motor, so you have basic idea regarding induction motor operation. So if you see, just I will not ask you, rather I will repeat this one. So induction motor, if you see its operation, normally we impress a three-phase balanced voltage at the stator terminals. Okay, and the motor is always having two parts. One is the stator part and another rotor part. So actually the rotation will be due to the interaction of these two magnetic fields, stator magnetic field and rotor magnetic field. Now what happens when you impress a voltage at the stator terminals? So the stator has three-phase windings, as I've said, and they are distributed windings. Okay, and the axis of these three-phase windings in space in the machine are 120-degree electrical apart. So then, if you see the MMF equation, resultant MMF equation, after impressing a balanced three-phase voltage at each of the phases, right? It will have a composite magnetic field which is rotating in nature, and the rotational speed, mechanical rotational speed, will depend on the number of poles and then frequencies, etc. And the electrical speed is always the frequency. So naturally, this rotating magnetic field, what will happen? This will cut the rotor conductors. So rotor conductors, because that is stationary at this moment, as soon as you, but rather at the instant you impress the voltage. So then whenever this field is cutting the rotor conductors, so what is going to happen? The rotor conductors or rotor winding will be facing some alternating flux linkage, right? That means changing flux linkage. Now, if you see Faraday's law, so naturally there will be an induced EMF in the rotor winding too. Now, there is an induced EMF in the rotor winding, and then you have to do one thing. You have to ensure that some current flows through the rotor. Now, how to ensure? Now, the EMF has to find some path to flow current. That means you have to short circuit the rotor terminals. Now, if it is a slip ring machine, you have to short circuit externally through the slip rings, or if it is a cage machine, they are inherently short circuited at the end rings. So naturally rotor currents will flow. Now when rotor current starts flowing, naturally rotor also generates its own magnetic field, own magnetic field. Now the interaction of the rotor and the stator magnetic field actually results in rotation. Now, on the other way of explanation is actually the rotor EMF will be, flowing rotor current, and rotor current will be creating rotor flux. Rotor flux will oppose the stator flux. Trying to remove the cause, and then we will try to follow the speed of the stator magnetic field, so that there is no flux cutting. So this way, anyway, you can explain the operation of induction machine. So now the major cause what we are finding here, is the change in flux linkage in the rotor conductors. That is actually causing the rotation, right? And other way, other sentence we are telling that the rotor conductors tries to catch the stator magnetic field in speed, so that actually there is no change in flux linkage. That means the rotation will be in the direction of the stator magnetic field, right? Or air gap magnetic field, whatever it is, right? So now the rotation depends on what actually. Then it is actually, if you see the mechanical speed only we will consider, because as I have said, electrical speed is always same. So mechanical speed, if you consider, if you have got the expression for synchronous speed. Synchronous speed is the rotational speed of the stator magnetic field or rotor magnetic field with respect to stationary axis. That means if you see, you have read also in your earlier classes of induction machine, that the rotor magnetic field speed with respect to stator stationary axis is also omega s, or synchronous speed. and the speed of the stator magnetic field with respect to stationary axis is also synchronous speed. If there is a speed difference, there won't be any steady torque produced. There can be instantaneous torque, but the average torque will be zero. That means if you design the rotor and stator with different number of poles, naturally you will not get any steady torque, pulsating torque, and that will result in no rotation or pulsation or jerking, etc. Right? So that is why number of poles for a rotor and the stator windings has to be made same. Now poles, you see, that is only valid for wound rotor machine because we are there making windings. Now in case of cage machines, there is no question of such because the rotor poles are created by the stator poles, and then they assume the same number of poles as the stator poles automatically based on the design of the bars, number of bars, etc., etc. So then actually, in order to control the speed or in order to vary the speed of induction machine, then that formula is the best. I mean, formula is what? 120 F by P. I think this one, 120 F by P. That's what you saw for the synchronous speed, right? S is 120 F by P. So NS is 120 F by P. So now, if there is a change in synchronous speed, then only there will be a change in rotor speed. As the rotor, as I said, it will always try to catch the stator magnetic field. Now, how you can change the synchronous speed? By changing either of the poles or the frequency of supply, right? Now, another factor still remains, that is what? The load factor. Now, this is actually, as you know, that the speed, the gross speed is like that. Say Ns equal to 120 F by P, and rotor speed will be almost equal to this. But if you go a little bit with accuracy, so you will find that with load also the speed changes due to the slip, and the slip is proportional to load. If the load increases, slip increases. But you know, then the equation for actual mechanical speed is actually ns into 1 minus s. That is what you see from this equation, definition of slip. Ns minus nm by ns, and you compute nm, you get nm equal to ns into 1 minus s. Now this slip also, you see, at full load is about 4%. Almost all, 99.9% of the machines. Maybe a few machines will have 5% maximum. And at no load, it is below 1% or 0.5%, like that. It's very negligible. That means we have a variation of 0.5% to 4% of synchronous speed. Now, with load, the variation is quite minimal. But for accuracy, you require that data. Otherwise, gross speed, actually, that is only dependent on this frequency and number of poles. Now, example, if you take a 4-pole machine at 50 hertz, so at synchronous speed, it will be 1500 RPM. Now, 4% of 1500 is only 60 RPM. And then 0.5% of 1500 is actually 7.5 RPM. So you have a variation between 7.5 to 60 RPM speed at 1500. That means per unit variation. So you don't get too much of change, because 4% is actually 96%. So 99.7 0.5%. So 99.5% to 96% variation. So if you ignore that, they are grossly dependent on frequency and poles. And if you take that, besides frequency and poles, there is a slip factor. So we will see all the things while see. Now look at this slide where we are finding that the methods. Now methods then the gross methods will be actually how to by changing the synchronous speed. Now by changing the synchronous speed is the method is pole changing. So you can do by pole changing also. If you change the number of poles, so definitely there will be a change in synchronous speed and change in rotor speed. And the second one is variable voltage, constant frequency. That is, if you vary the voltage, you will see actually. If you vary the voltage, right? Voltage. at same frequency. Then also the speed control or speed can change. And then the third one is vary the frequency, direct variation of synchronous speed, right? And then the other gross methods are actually constant volt by Hertz control. So that we will see what are the difficulties in the above three techniques. And then that will be overcome by these methods, maybe open loop and closed loop for constant volt by Hertz. And then there can be other methods like constant air gap flux control and field orientation control. So these are the gross methods of controlling the speed of induction machine. So through pole changing, through voltage, variable voltage at same frequency, variable frequency, and then you can have constant volt by Hertz, open loop and closed loop both, and then you can have the other the method like constant air gap flux control and field orientation control. The last two methods are quite accurate methods, eh? And the one below it, above it, is actually is a good way. I mean, it's an easy implementation of fairly accurate control. Okay, and then the other methods in the top are actually at the top are the gross methods. Okay, then we come to actual implementation of the one by one method. So to understand the speed control technique, we must understand the actually equivalent circuit. Now, equivalent circuit you have already read, and the first one is actually the exact equivalent circuit where we have. আচ্ছা হ্যালো সোমনাথ, আমরা এখন ক্লাস নিচ্ছি একটা, আমি তোমাকে ফোন করে নেব, হ্যাঁ, যখন ফ্রি থাকবো, ঠিক আছে? এরপরে আমি তোমাকে ফোন করে নেব, ঠিক আছে? So you see that the exact equivalent circuit is actually this one, where we see that the XM and RM, this actually the no load parameters are placed at the middle in between the stator leakage parameters and the rotor leakage parameters. Now this exact equivalent circuit is fine, but while computing torque, right, this makes life a little bit tedious. So you have to go by calculating the exact equivalent resistance, and then divide voltage by impedance, equivalent impedance. You get stator current, and then you can get the rotor current, and then calculate torque as IR square RR by S into 3 by omega S. So this gives you a little bit say calculative effort, more calculative effort, or computational effort requires. So in order to avoid that, since the stator leakage impedance are, I mean, not of the order of this RM and XM, right, are much lesser, actually much lesser, maybe 100 times or 50 times lesser. So then we can shift this branch to this starting, I mean, at the end of the stator voltage, and the accuracy is almost maintained within, say, 3 to 4%. So therefore we go by this way. So the value of magnetization inductance and value of RM core losses, and then XM is quite large compared to RS plus XS. This XS is nothing but XLS. XLS. Don't write XS. It will be XLS. It's a printing mistake from my end. And the magnetizing voltage is the same as the input voltage. That's saying that Vm equal to almost Vs, because voltage drop is negligible if the impedance is less. Therefore, the equivalent circuit can be actually approximated from this to this. Now we have done far more approximation by removing Rm also. Normally, the ratio of Rm to Xm at rated values about 4 to 5 or 3 to 4 at least. So you can easily remove this Rm, and I'm sorry, this XM is not written here, it will be XM. So then the equivalent circuit looks like this: XLS, RS, XLR, and RR by S. Oh. Just a minute. Hello? Okay. Okay. So I'm taking classes. So in the evening we will I'll contact you regarding that problem. Huh? Okay. 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 You take care. Huh? All right. So then you see that XLS, RS, XLR, RR by S. So this actually in between you have a stator side, then air gap, and then rotor, right? And this is your output power P0. So that you have read also. Now from this circuit, you can easily calculate rotor current. Rotor current is actually BS by this impedance, rotor side impedance. That means RS plus RR by S plus J XLS plus XLR dash. Right. So now magnitude wise, if you compute, it would be V by square root under RS plus RR by S square plus XLS plus XLR dash square. Okay. So this is your rotor current magnitude, right? And from that rotor current magnitude, you can compute torque very easily. That I have said 3 by omega S into IR square RR dash by S. So after computing that, this looks like the equation looks like this: 3 RR squared RR dash square VS S omega S RS plus RR dash by S plus XLS plus XLR square. So now this torque we find is a function of slip. Let us say other parameters are constant, omega S, XLS, XLR, RR dash base, all are constant. Then torque becomes a function of slip only. And if you plot torque plus the slip in the region is varying from 0 to 1, means synchronous speed to starting speed, you get a speed torque characteristics like this. Whatever I have is the TD. I mean motor characteristics. It will be TM actually. This is motor characteristics, right? Now if you have characteristics like this, right? So then these two characteristics can intersect at some point, and that becomes the operating point of that particular load, right? That means if the load characteristics is the red line and the motor characteristics is the black line, so this will operate at a point where Tm equal to TL, and then corresponding torque and corresponding speed will be delivered to the load. So now supposing you shift the speed or shift the torque to this location, so naturally then it requires the speed control. It has been written also. So whenever you change this operating point from one to the other, you require a speed control. So speed control or torque control, and when speed is controlled, so naturally you need to control the torque sometimes if the load torque is not a constant torque load, right? If the load torque is not a constant torque load, so then both speed and torque control will be required. Okay. Now this is where we require the speed control of induction machine or speed control of any machine. So shifting of operating point from one to another will require always a speed control for induction for the machine. Okay. So then you see that again we see the torque equation, torque speed variation, rather torque equation. So then this torque equation again I am rewriting. Now, as I have already showed you that the variation of operating point can lead to variation of torque as well as variation of speed. So now keeping all other things constant, now torque is dependent on voltage also. So varying voltage also, as we are seeing, a T is proportional to Vs square, keeping all other things constant. So therefore, the second method, what we shown there, what we had shown there, that is by varying the stator voltage. So that is also valid. That means that if you vary the voltage, naturally your speed and torque both can vary. And then this part, omega s, if you just split up, it will be like this: 2 by p into omega. Omega is 2 pi f, so you get 4 by p into pi f. So naturally it is frequency. So generally the torque will depend on frequency also. And then pole also, pole P. So that means these three methods, what we showed there, by varying the pole, number one method we have indicated here, by varying the voltage, number two method we indicated there, and then number three is by varying the line frequency. So any of these three, or both, or combination, all, you can make to vary the pure torque and the speed of the machine. So I think till now you have understood the basic philosophy. Now we will go for later on. We will show what is constant torque on power later, but only this one. So is it okay? All right. Because I'm moving fast. This slide technique actually makes things faster.
Okay, sir.
Okay, huh?
Yes,
Okay.
yes, sir.
So now you see that we will see the pole changing. Pole changing. So some of them are not there. So I had to handwrite. So normally, as I said, what is a pole? Induction DC machine, you find poles very stringently. You can see from outside poles, right? It's the extended part of the yoke, inside the yoke, you can say, stator. But here, poles are mainly coils. So if you open, I think some of you have, all of you, I think, probably have performed the experiment, start AC machines. There, you had seen the coils in the stator slots. They are in the form of some coils. Winding in the stator slots are in the form of some coils, right? So these coils actually forms poles. If you assume that anti-clockwise rotation is say south pole, right? The clockwise rotation will be north pole when current. Then see, we have shown some winding cross sections, and then the formation poles. Say clockwise rotation here, you see north pole. Then after anti-clockwise is south, clockwise again north pole. So 1, 2, 3, 4. It's a 4 north and 4 south, 4 pole connection. So now if you have coils like these, 4 coils you have, and you connect like this. Say A is connected to then this one, third one, right? And then it becomes AB. It becomes say 2 terminals of 2 coils, and then CD also like this. CD also like this, clockwise, and then this clockwise CD. And if you connect A and C together, B and give the C and B and D, that is what you have seen. Okay. So we get actually 8-pole structure, NS, NS, NS. So just alter the structure, say from A.
স্যার ফার্স্ট পার্টটা বুঝলাম না স্যার, ওই কানেকশন গুলো
কেন কি অসুবিধা হচ্ছে দেখো, স্ক্রিনটা তাহলে তো বুঝতে পারবে যে ক্লকওয়াইজ অ্যান্টি ক্লকওয়াইজ, ক্লকওয়াইজ অ্যান্টি ক্লকওয়াইজ। বুঝা যাচ্ছে? ক্লকওয়াইজ
স্যার এই বিটা যাচ্ছে ফার্স্ট দুটোতে নাকি?
এটা ফার্স্ট আর থার্ড, দেখো 1, 3 সেকশন আছে।
ও আর সিডি তে হচ্ছে 2 আর 4। ও দিও একটাতে ক্লকওয়াইজে পাঠাচ্ছেন আর একটাতে অ্যান্টি ক্লকওয়াইজ, না ও দুটোতেই ক্লকওয়াইজে পাঠাচ্ছেন?
ক্লকওয়াইজ, কিন্তু মাঝের জায়গাটা যেটা সেটা অ্যান্টি ক্লকওয়াইজের মতো হচ্ছে।
ও মানে অ্যান্টি প্যারালাল হচ্ছে দুটো,
অ্যান্টি প্যারালাল, হ্যাঁ।
ও ওকে ওকে।
You can like this parallel is mode, so B and C are connected, right? B and C are connected. Physical কি হবে? B কানেক্ট করে AD তে সাপ্লাই দিতে হবে, অথবা A আর C তে কানেক্ট করে আর B তে কানেক্ট করে প্যারালাল সাপ্লাই দিতে হবে। Any of these two connection, from this 8 poles. এবারে সেম কয়েল ঘুরিয়ে দিলাম, A আর তার সঙ্গে এই যে ফার্স্ট আর থার্ড একই আছে, কিন্তু কানেক্ট করলাম কিরকম, বি আর ডি তে কানেক্ট করে দিলাম, বি আর ডি, রাইট? তাহলে কি হবে দেখো, যে মাঝের যে সাউথ পোল গুলো হচ্ছে সেগুলো আর হবে না, actually north south alternate হয়ে গেল। বুঝতে পেরেছো?
স্যার আগের বার
Just to
অ্যান্টি প্যারালেলের জন্য সাউথটা হচ্ছিল আর মানে ক্লকওয়াইজের জন্য নর্থ।
মাঝখানে সাউথ হচ্ছিল, মাঝখানে সাউথ ক্রিয়েট হচ্ছিল, এখানে
হ্যাঁ।
মাঝখানে আর ক্রিয়েট হবে না, কারণ মাঝখানেরটা একই ওয়াইন্ডিং, দুটোই দেখো উপর থেকে নিচে যাচ্ছে। ওইখানে কি হচ্ছিল, বাঁ সাইডে উপর থেকে নিচে যাচ্ছিল, আর ডান সাইডে ইট ওয়াজ ফ্রম বটম টু টপ। সো উই হ্যাড এ
মাঝে দুটোই হচ্ছে সেম ডিরেকশনে বলে, আর সাউথটা হচ্ছে।
হ্যাঁ।
ওকে।
So actually the generation is like this, NS 4-pole structure. So just we connect in different way. We have to make BD and supply from AC in series, or if you want to make parallel, AD and then BC, then give a parallel supply between A and B. So then actually you can create the different number of poles if you have the access of the each of the coil, right? So then actually what happens to the speed torque characteristics? Then this one. So for 8-pole characteristics you have like this, and 4-pole you have characteristics like this. So naturally if you have a load torque varying like this, so you can shift the operating from A to B or B to A depending on necessity. If you want to increase, you can shift from B to A, and if you want to decrease, you can shift from A to B. This can be possible with 2-pole and then say 6-pole. Different modes of connections are to be made. Okay, so I have shown it for only 2 coils. So naturally then,
বলছিলাম স্যার যে কানেকশন দিয়ে তো আমি শুধুমাত্র হচ্ছে যে অর্ধেকই করতে পারবো, মানে ওর থেকে বেশি তো আর করতে পারবো না, মানে 8 পোল থেকে যে 4 পোল করতে পারবো বা 4 পোল থেকে যে 2 পোল করতে পারবো, মানে আমি বলছি কানেকশনটাকে যে অল্টারনেট করে ওর থেকে তো আর
তুমি যদি রিমুভ করো 2-একটা ওয়াইন্ডিং 6-পোলও করতে পারবে। ওকে,
আচ্ছা আচ্ছা, মানে তখন আমাকে হচ্ছে ওয়াইন্ডিংটা চেঞ্জ করতে হবে। আমি বলছি যে মানে শুধুমাত্র যে কানেকশনটা চেঞ্জ করে তো অর্ধেক করতে পারবো, মানে এই যে দুটোই অপশন আছে।
না, দুটো নয়, তুমি একটা বাদ দিলে তুমি আবার মানে 6টাও পাবে।
হ্যাঁ,
আগেরটাতে একটা বাদ দিয়ে দিলে, হ্যাঁ, সুতরাং 6টা পেতে পারো। তো 8টাও পেতে পারো, 4টেও পেতে পারো, 2টো পেতে পারো। So you can see the number of poles. That's what my point is. Okay, by changing the connection of the coils. Now the thing is that this has got some limitations. How limitation? First of all, actually, I was talking in the just at the beginning of the lecture, that when it is a squirrel cage machine, right? Squirrel cage machine. So the rotor will assume the same number of poles of the stator automatically. So this can be easily applicable for cage machines. But in case of say slip ring machines, you need to change the rotor connection also. Like rotor connection is a rotating body, so actually it will require slip rings and brushes to bring all the coils outside. So naturally shaft extension will be too large if you have say many number of coils, right? So then this is not exactly feasible for the slip ring type of machines. Secondly, you see the shifting of speed is in steps, and it is almost in discrete manner. Say if it is a 50 hertz supply, 2-pole means 3000 rpm, and then 4-pole means actually 1500 rpm, 6-pole means 1000 rpm, 8-pole means 750 rpm. If you want a speed around say 2500 rpm, it is not possible. So only by discrete steps, speed changing by discrete steps was possible. So this is actually a primitive method when all other controls were not available. So people had no other means but to implement this in this fashion, so that at least some speed change can take place, and they can adjust their loads to operate on this discrete speed modes. Okay, but it is not very smooth. So nowadays actually this method is not used with the advent of this power electronics and then high-speed control technology, high computational ability, wise, processors with high computational abilities. So, this method has almost obsolete because actually we can do it very smoothly with the help of other techniques, right? So this was primitive method. You see here, there is no implementation of any switches, power electronics, only by say contactor switching. The shifting of the contactor switches that can take place to vary the speed. So this method is having that limitation, and then it is not used these days, almost not used these days. Now, second method we will go, where we use that variable voltage at same frequency. We saw that torque is proportional to voltage square. So I think that I must stop it here, because this PhD Viva was going on there. So I'm a member, so I have to be present there. So I think we will start it from here, because this itself will take say 20-25 minutes time. So if I finish by after 5 minutes, it will not give you any sense. Okay. So today I wrap up here. So I think you have another class. Maybe I will take next Monday 2 hours at a stretch. So I think we can go little far deeper and cover more items. Okay. So you can send me your roll sheet today by indicating whoever is present today. So I'm stopping here on this one.
Okay.
Okay. Okay. Okay, you send me the roll sheet,
Okay, sir. Thank you, sir.
Okay.